Welcome back to Mechanics and Control of Robotic Manipulator. This is lecture 12. So this is on statics, in the sense static manipulator, or you can say static conditions of robotic manipulator. So here we will see if this is the freezing position, if I have any end effector load or even the body which is are there, which is right now we are not seeing the inertia, but right now if you see that if end effector has any force or moment, so what would be the torque required to each motor so that it can actually stay in the same pose. So that is what we are going to call here as a static. So this particular lecture we're going to talk about statics. And then since it is a serial manipulator, and in the sense serial spatial manipulator, there would be some kind of collinearity between links, or you can say perpendicularity between links with respect to joint, that would be actually prone to be a singular. In the sense what happened, the Jacobian matrix may be actually singular, in the sense the determinant of Jacobian may be 0. What that means, for example, you have, this is a 2R serial manipulator, so now you have actually two active joints, but when you see at the extend position, in the sense extreme position, so you can see that even this motor is there, but this is the position, so you can see that this degree is lost, right? So this is what we are going to call as a singularity here. But whereas if you go to a you call a parallel chain, so then there would be another kind of singularity will come, where in that singularity you would get additional degree of freedom, in the sense you will get additional motion. For example, in this case, this is a 5R, you can say 5R parallel manipulator. Now these two joints are actually collinear, then you will get the serial singularity. But if you imagine, if these two are actually collinear, what happened, this point can actually go up and down, in the sense although you are not moving anything, this joint actually this particular point will actually influx, in the sense it actually gain one more degree of freedom. So that is what we are actually trying to see in the singularity at the last. But right now we are interested to see what is statics, in the sense if I actually see the same serial manipulator, if I give some force at the end point, so what would be the torque to you can say provide in two motors, or you can say two joints, in order to maintain the same you can say configuration. So that is what we call you can say statics in this particular case. So we are not actually bringing the body weight or inertia, but we are actually seeing even the statics here, we are not even bothering about the you call gravity. So then the gravity balancing, or you call static balancing, that would be considered in the last. Right now we are not interested to see that, because this is actually in the single go. So what we have seen in the last lecture, we have seen the differential kinematics. So we are actually going ahead with the differential kinematics to the statics. So that is the flow we are actually seeing. So right now we assume that this is statically balanced, but if I apply any end effector load, what would be the torque to be you can say provide each joint, so that this particular manipulator will be stay back that particular configuration. That is what we are interested to see. So in that sense, we are actually coming back with the same you call disclaimer, and we are actually going further. So in this particular short lecture, we would be seeing three contents. So statics is important in this particular perspective, and the singularity very lighter way we would be introducing. So since the static is coming from something background on differential kinematics, so in the initial few slides we would be talking about differential kinematics in general. So that is what we are going to see. So you can see that the forward kinematic model we know, which is nothing but mu is actually function of q, where mu is actually your end effector points and as well as orientation, whereas q is your joint space variable set. So this is the relation which we got it. And if you take the inverse, in the sense the function inverse, that is what going to be you call inverse kinematic model, right? But what we know further, we know forward differential kinematic model, where you take the function whatever you have, that you take a differentiation with respect to time. So then the mu dot will come as a dou you can say function of q divided by dou q into q dot, right? So that is what we are going to call as a forward differential kinematics, where that partial derivative of that function with respect to the joint space variable we call Jacobian matrix. So now this is also we know. So then what we are actually like interested, we are interested to simulate or analyzing the system. And if we are actually like go back, so I want q dot, then j of q inverse into mu dot, that is what inverse differential kinematic model, that what you call controlling the manipulator, right? So that is what we are actually like seen, and this is what we are actually like seen. If it is the, you can say, joint axis is not exactly 6, if it is in a spatial, then that would be a rectangular matrix, then we would use the pseudo inverse. Even in the last lecture we were discussing about the pseudo inverse, how we can get with the help of Moore's Penrose we have seen, right? So these all actually like we have seen. Now what we are actually like interested, so we are interested to see, I'm giving a simple 2R serial manipulator example. Okay, so now I am actually like saying that there is a you call the end. So I am actually like seeing that this is what your x1 and this is what your x2, and now I am actually like showing that there is a force F. So that is actually like with respect to, so x naught is actually like known. So in the sense theta is known and the quantity also known. So this I call psi. Okay, so then you can see this is theta 1 and this is theta 2, and this is actually like px and py. So these all would be known. So but right now what I am saying, that I am actually like giving fx, this is f cos psi, and fy is actually like f sin psi. So these are all known. And if we assume that this is the, you can say, the particular configuration, this particular configuration supposed to be froze at this particular, you can say, configuration, then you should actually like provide some torque, you have to provide in such a way that this would be maintained. Okay, the torque direction I am putting in the, you can say, positive direction of the rotation, but it can be actually like negative positive based on the f. Okay, so right now what we are interested to see, what would be tau 1 tau 2 in order to maintain this, in the sense what we know. So we know, like, if you see the you call the work to be done or work done at the configuration space, that's supposed to be equal to the work done at the operational space. That is what the basic principle. In the sense, I said the sum of work happened on the joint space supposed to be usually like supposed to be equal to the sum of the work done at the, you can say, operational space. Right now we are not bothering about the losses or the dissipation. In the sense, this is supposed to be true as per the energy conservation, right? And further what you can see, so further what you can see, one more thing you can see, like I'm just taking a body, and if this body is actually like I call link k, or you can say link I, whatever way you can see, then you can see that that would be associated with I minus 1 and I, and I assume that there is a force which is actually like happening here, so I call that is Fi. So then Fi with respect to I frame, if I know, then you can see that this is the single link. So then this force is acted, then if this is supposed to be equilibrium, then what's supposed to be, then there would be a opposite force, and you can see that that's supposed to be presented. So in the sense, you can see that this is actually like Fi with respect to I minus 1. So this is in the sense, so you are actually like seeing that this particular point supposed to have opposite force, or if you actually like transfer the force, that's supposed to be equal. That is what we are interested to see. So in the sense, what you will get, so Fi with respect to I plus 1 and Fi plus, or you can say I, this supposed to be equal. So in the sense, this sum supposed to be 0. That is what we are trying to see. In the sense, equilibrium f equal to 0, right? This equation we are trying to see. Similarly, if I have this force and I have some moment, then what I can see, this point supposed to have a you can say moment. The moment I am writing as ni. So then the ni with respect to I minus 1, or you can say, sorry. So this is supposed to be I minus 1, right? So then that also supposed to be the same way. So it is actually like a sum of, you can see, this is I call the p vector. So then you can see that so p I to I, so I put this, okay, this I, this is, so I'll come back with the equation, right equation, but this is actually like a cross multiply with fi right? So these all actually we can, so in the sense sum of you can say moments supposed to be 0, right? So this is what the equilibrium condition. So if I apply that equilibrium condition, you can see that this is, you can say, force vector, and this is an you can say moment vector. This sum supposed to be 0 as per the static equilibrium case. So in the sense what we are seeing at link I, so link I would be having I and I plus 1 as the frame. So if I have a force balance, then what I can see, the force happening at the ith frame and I plus 1 frame supposed to be, you can say, equal. In the sense if I take a vector addition, that's supposed to be 0, right? So similarly, if I take the moment vector addition, that also would be 0. So then the moment is not only this you can say input, or you can say the moment at the point, but there is a force also that then that would be also added. In the sense I see, so this is what the point. So here there is a force which is I call I plus 1, and with respect to I, that is I know. So then you can see this is the I plus 1 with respect to I, the position vector, and here there is a moment which is I plus 1 with respect to I. So then if I see this point, so then this point supposed to have n I to I, that's supposed to be equal to the vector which you can see the moment which is actually generated of this, and then this moment, in the sense this force also will generate. That is what the equation which is given. So now these all actually like no, and we will actually like go for the forward you can say propagation for the velocity, and the force you can say backward propagation for the you can say force balance. That all we will see in the upcoming lecture, but right now you know this is the relation which we wanted to use, right? So in the sense if I rewrite this equation, what you can see, the propagation you can do it. So in the sense, so I know the end effector, so the end effector point force with respect to I plus 1 frame, if I know, then what I can do, I can actually like bring the rotational matrix, in the sense, so I plus 1 with respect to I, if I know, then what I will get, so I plus 1 to I, right? So this force if I know, then what that's supposed to be equal to the joint force on the ith frame. So this is not. So similarly I can extend, if I know this I plus 1 to I plus 1, the end effector you can say moment, that I can actually like bring it back to here. Okay, this is nothing but you can see I plus 1, so this is we can obtain, and you know this relation, so this also we obtain. Then you can actually like take the you can say vector you can say cross multiplication, so where this p vector is known, so p vector of I plus 1 with respect to I is known, then I can actually like get it this. So this is what you can see, the you can say backward propagation of the force, or you can say force balance. So then you will get these two equations. So how we have done the you can say velocity propagation. So we have done this. So we have done this, right? So you remember this, I hope. So that's why I have actually like done this straightforward. So right, so this is what you said, if it is a rotary joint, and this is the linear velocity propagation, right? Angular velocity propagation, you know, that is also like we have done like this. So this is forward propagation where we start from I to I plus 1, and this is a backward propagation where you have start from I plus 1 to I. That is the you can say difference. And this is what we have seen as if it is a rotary joint. This is the angular velocity propagation, and this is the linear velocity propagation. So similarly, this is the force you can say what you call backward propagation. And you know, as per the rotary joint, so what would be the moment? So that would be actually like you have n I plus so I to I. So this would be getting, that would be having three moments. I call nx, ny, and nz. So as per the rotary joint, the joint axis is associated with what? So the z-axis, in the sense the nz is what you call the torque. So similarly, if it is a prismatic joint, then what you will get? So it's a prismatic joint, then you have actually like Fi to I, that would be Fx, Fy, Fz. So and as per the prismatic joint, the joint axis would be z-axis, in the sense the your force would be Fz. So like that you can actually like get it all the equations, right? So that's what we are actually like trying to see, but right now we are not seeing any example. So what we are seeing, we are actually like seeing the general equation, Okay, so this is what we obtained as a backward propagation or back propagation model, right? So now we can actually like go even further. So what that means, we can actually like go further to additional. So I am actually like using the work, you can say principle, in the sense conservation of you can say energy. So in the sense work is the dot product of the vector force or torque and vector displacement, this you know. But as per our understanding, as per the conservation of energy, what you know, like the you can say work done at the joint space is equal to the work done at the, you call the operational space. So the operational space force and you can say moment I am writing as a f as a vector. So that would be fx, fy and fz, and mx, my and mz. So this is actually like 6 cross 1, and the delta mu is actually like what you have the change in displacement, that is also like you can see delta x, delta y, delta z, and delta alpha, delta beta and delta you can say gamma. Okay, that is also 6 cross 1. So this is actually like work done at the, you can say, operational space. So the work done at the, you can say, configuration space, that would be tau 1 to tau n, and the delta can say delta q I can write as a delta theta to delta theta 1 to delta theta n. If I assume that these all joint are actually like rotary joint, then tau 1 to tau n. If any joint are actually like you can see that is a prismatic joint, that then that would be f1 f like that will come. So now this is the work done at the what you call configuration space, and you know this is a dot product. You can write the dot product with the help of you can say simple vector multiplication. So since it is actually like dot product or inner product, that you can rewrite as a transpose of that vector into that, and you have already obtained the delta mu as, so what, so j of q into delta q, right? This equation you have already obtained. That equation I am actually like substituting it. So what you will get, so the delta q go away, so the tau transpose is actually like f transpose of j of q, and you take the transpose throughout, then tau is actually like j of q transpose f. So in the sense, if you know the end effector position and end effector forces and moments, so then what you can actually like see, you can see what would be the joint you can say forces and torques. Okay, so in the sense what's supposed to be provided on the input joints, so that you can maintain even you apply some force and moment on the end effector, the configuration would be retained as the same. And here the provision is the j of q is supposed to be known, and the j of q is actually like here just a transpose, and you can actually like see that the j of q is actually like available, and j of q transpose also available. In the sense you can get this relation. So this is what we are actually like calling as actually like you can say static relation, or you can say statics of a robotic manipulator. The same thing you can obtain even with the principles of conservation power. So what that means, so it is again dot product of you can say force and you can say velocity vector. So that is what we are seeing, and again as per the conservation of power, the configuration space work, or you can say power whatever done, that's supposed to be power to move the robot at the operational space. In the sense I said the tau transpose, I will directly I won't write directly. So I say that this is actual configuration space. So tau into you call I'll write as this one. So tau into actual like q dot is equal to f dot into mu dot. So this relation we get it. So that is what we are actually like writing, and this again I can write tau transpose q dot is equal to f transpose into mu dot, and you know mu dot I can write as j of q into q dot. That relation I can substitute, and then I can actually like bring it back the same relation what we obtained, and then take the transpose throughout, and you can actually like get it that, right? So this is what we are doing it. So now we will actually like go forward. So what you can see that the singularity is what we have discussed in the last you can say introduction. So what is singularity? Singularity is generally speaking, if we assume that the robot is redundant or not, it is actually like some configuration what we will feel it, the Jacobian you can say would be singular, in the sense the determinant would be 0. So what that means, so some you can say the linear independent equation become something as a dependent. For example, this equation, you can say this is what my end, you can say the configuration. So you can see that this equation is actually like redundant, where theta 1 would be something So you can see even here, but the theta 2 is actually like a 0. In the sense, if you want to write this equation, what you can see, that is actually like L1 C1 plus L2 C2, sorry, L2 C1 only, because C2 is 0, right? So then you can see that earlier it was linearly independent, but now you can see that it is actually like a dependent. What that means, the Jacobian matrix, so it would be minus L1 S1, and here also minus L2 S1 and minus L2 L1 S1, right? So in the sense, I'm just writing the other way around. Okay, I'll just write it the same way. So this is actually like a minus L2 S1, and the second term is actually like minus L2 S1. Okay, so in the sense, you can see this is actually like L1 L2 are constant, so it is purely dependent on only S1, right, this row. So similarly, if I actually like write the other one, so this is what you can see. So you can see that it is actually like very similar, right? So in the sense, if you actually like take the determinant become actually like what you call, it is actually like going to be 0. Okay, so that is what we are actually like interested to see here. The sense theta 2, if it is 0 or 180, what happened, that would be actually like making one joint is actually like useless. In the sense, it is not having any what you call role on that particular joint. That is what we are saying, that the end effector is loses one or more degrees of freedom. So you can see that the theta 2 is not coming in the x and y equation, right? So that is what you can see. So what you can see, it is L1 C1 plus L2 C1, and this is L1 S1 plus L2 S1, right? Where L, you can say the theta 2 role is not at all coming in this picture. So that is what we are calling in the serial manipulator, which is nothing but singularity. So when you take the Jacobian matrix, you can say the determinant would be 0. So when this can happen? This can happen if the two prismatic joints become parallel, okay, and the two revolute joints also become identical. In the sense, if it is actually like overlap with one to another, so then you can see that the collinearity will bring that as you call singularity. So in the sense, what one can see, the singular position must be avoided because the velocity required to move the end effector become theoretically infinite. Why? So you know the Jacobian matrix determinant is actually like 0. So in the sense, the J inverse actually like become infinity, right? So that is what we are trying to say. So and what we can see, that singularity can happen in two places. So for example, I am taking a 3R serial manipulator. This 3R serial manipulator, the singularity can happen at the workspace end, extreme end, that is what you call boundary. Then the boundary can actually like reach, when you extend the complete point, you can see that one or two joints are actually like lost their degree. So that is what you call workspace boundary singularity. But even the collinearity can happen within the workspace. For example, these two are collinear, then you can see that within the workspace also like would be having a singularity. That is what you call workspace interior singularity. So these all we will see in detail in the upcoming lectures, but right now we just give an introduction to, you can say, boundary and interior singularity. Okay, so in the sense, you can see that this singularity can be obtained with the help of what you call the Jacobian matrix. So if it is actually like square matrix, you take the Jacobian determinant and equal to 0, then what condition that would come, that conditions are actually like, you can say, singular positions or singular points. When this matrix is actually like rectangular, then you can take, so whichever matrix is giving the smaller size, so J transpose into J or J into J transpose, that way you can take. In the sense, if M is actually like greater, in the sense, so you have actually like 6 as your operational space variable, and you have actually like 5 is your, you can say, joint space variable, then 5 cross 5 which is giving, then that is J transpose into J. So that determinant you can take, and you can actually like find the singularity point. Whereas if the other way around, you have actually like 6 but 7 variable are there, then you can take it the other way around. So that determinant you can substitute equal to 0, and you can find the singular position. And these all actually like what we are discussing on the serial manipulator, that is what our interest. Okay, So now for example I have taken the 2R serial manipulator, and you know like this is what the Jacobian matrix, and I already shown the Jacobian inverse also. So then if you take the determinant equal to 0, so you can see that this is what the final end, which is you can say retained. And if that I equal to 0, so L1 and L2 are not 0, then what you can see, sine theta 2 is actually like 0. Then you can see theta 2 is actually like n pi, so where n is actually like varying 0 to, you can say, infinity. So that is what we are actually like calling, in the sense you can see the two immediate conditions, you can see 0 or pi. So 0 means what, you can see these two are actually like collinear, in the sense it is extended. So this is one boundary singularity. Then you can see this is actually like folded, what happened. So this is what you can see as a folded condition. So I am actually like showing that the L1 is greater than L2. So you can see this is another boundary, but this is also singularity, where it is actually like the theta 2 is pi. So now here also you can see this joint is actually like lose its degree. So that is what you can see, this can rotate with this extended position, this also can rotate with this extended position, and the, you can say, folded position. So this is what we are calling the singularity. And here we have just introduced a very lighter way what is singularity and what is serial singularity. But in upcoming lectures we will discuss more detail about the singularity. But right now we have actually like talk about the singularity can be obtained by substituting or equating J of Q determinant equal to 0, then you can find the singular positions, right? So if it is a rectangular matrix, you can actually like use the J transpose of J, or J into J transpose that square matrix determinant you can equate to 0. And what we have seen so far, we have seen the static relation. For example, I have end effector force, so this particular configuration should be retained. What would be my joint force and joint torque need to be provided. That's what we have actually like seen so far. And the next lecture we will see a little more insight to the body, in the sense we are going to see if the inertia is coming into a picture, or you can say the mass of the body we consider, and we have considered further end, then we will talk about rigid body and the rigid body dynamics of, you can say, manipulators we are going to see. That is what the next lecture. And if you have any doubt, you please post an email to me, then we can actually like address those all. With that, I'm actually like closing this particular session, and we'll see on you can say Friday live session. And with that, I'm actually like closing this particular session. See you then. Bye bye. Take care.